The score now stands AA 1150, PMS 1175. So, for 100 points and the match, please turn your attention to the formula on the screens. Solve the equation.
Holy crap.
It looks like something they found on the ship at Roswell.
Come on, think. Leslie?
10 seconds. PMS.
Sorry, I panicked.
Then guess.
8. 0.4.
I'm sorry, that's incorrect. AA, if you can answer correctly, the match is yours.
He doesn't have it. He's got squat.
AA, I need your answer.
The answer is minus 8 pi alpha.
Hang on a second. That's not our answer. What are you doing?
Answering question. Winning physics bowl.
How do you know anything about physics?
Here I am janitor. In former Soviet Union, I am physicist. Leningrad Polytechnica. Go polar bears.
Now, it's actually surprising how Sheldon couldn't solve the problem, or didn't know how to. Because Sheldon is a theorist, right? It makes sense how Leonard can't solve it since he's just an experimentalist. But you would expect Sheldon to be able to solve this problem. But fortunately, we can solve this problem because we know the steps. So here's how to actually solve the problem on the screen. Now, for context, this is actually what's called a Feynman diagram. And it's used to calculate the probability that two particles pretty much bounce off of each other. So here we have an electron and a muon. They come together and then they just bounce off each other. And we want to find the probability that this happens. And the probability for this happening is known as the matrix elements. And we write that like this. Now here, this term that you see in this equation, the square root of 4 pi alpha, it's kind of weird how it's written like that. Because for those who don't know, alpha is just called the EM coupling. It's equal to E squared over 4 pi. So this is just the same thing as saying E. So they just kind of wrote it in a bit more obtuse way. But in most textbooks, you'll see it written as just E, where E is the charge of where E is the elementary charge. But with all that being said, let's actually solve this equation, and here's how. So here I've written down the equation down below to make it a bit more easier to see. Now, a small thing is that the writers of the show made a mistake in the equation given. There should be a negative sign right next to the IG mu nu, but it looks like they forgot to include that. So that's just a small mistake that they made, but we can just continue carrying on by adding that negative sign right next to the IG mu nu. But with that added, here is the right equation, and we can actually solve the integral pretty easily, because we know that the integral of dx of f of x times delta of x minus a is just going to be equal to f of a. So basically, x is going to equal a, sort of. So using that logic, this means that q here has to be equal to P1 minus P3, right? And here the P1 minus P3 is sort of functioning like that A. So Q would have to be equal to P1 minus P3, just like how this X would have to be equal to A. So that means that our delta function would then just become P2 minus P4 plus P1 minus P3, since Q is P1 minus P3. And that actually makes us done with the integral. We can just remove this integral now, and we have our answer, pretty much. That is the solution to the integral. However, we still haven't simplified all of this down, so we still have to do all of that, but just the integral itself is a pretty straightforward thing to do. So we can sort of analyze this delta function to see if it makes sense. This delta function tells us that P1 plus P2 equals P3 plus P4. Because the delta function is just going to be P1 plus P2 minus P3 minus P4. And this delta function is only going to be non-zero when P1 plus P2 equals P3 plus P4, because this is just the same thing as saying P1 plus P2 minus P3 plus P4. And delta functions are only non-zero when this side equals this side. So when P1 plus P2 equals P3 plus P4. And this is just momentum conservation, right? Because it's telling us that the momentum of this electron plus the momentum of this muon will be equal to the sum of the momenta of the outgoing particles. And this makes logical sense. Also, that d to the 4q should go away since we've already done our integral. So yeah, we now have this over here, and this is our answer after we've done our integral. Now, in Feynman diagrams, the part that we are usually interested in is what's on the inside. It turns out that all Feynman diagrams give us a contribution of a delta function scaled with some factor of 2 pi to the 4th. So what's the non-trivial part of the Feynman diagram is what's in the yellow over here. And this is what we actually want to solve. Now, there are some problems with this Feynman diagram. First of all, it doesn't tell us the spins of the electrons and the muons. So we can't really solve it yet without knowing the actual spins of them. Because we do have S1, S2, S3, and S4, but it does not specify what those values are. So what we can do here is we can pretty much just assume that they have some particular values of spins, which we will do to get our answer. Also, what we are going to do is we know that this equation over here it's pretty long, it's pretty janky. So what we can do to help us simplify this equation is by using what's called the high energy frame. So we know how E squared equals P squared plus M squared. Well, if we have a high energy frame where we have particles traveling very, very fast, this means that P squared is much, much larger than M squared. So M squared can be approximated as 0. So by working in the high energy frame, we can treat the particles here as being massless, meaning that we pretty much have Bob scattering instead of electron-muon scattering. The Dirac equation, which describes electrons, simply reduces down to the massless Dirac equation. And the gamma matrices, by the way, this should be a downstairs index, can actually be written in terms of the poly spin matrices, where we have like each component of those or each one of those gamma matrices. Here's the example for M equals naught. And this bar on top of the polyspin matrices just means that we are going to be conjugating, or not conjugating, it just means that we are going to add a negative sign pretty much next to those spin matrices. So like sigma mu is going to be equal to, well, 1, then sigma 1, sigma 2, sigma 3, and then sigma bar mu is going to be equal to just 1 minus sigma 1 minus sigma 2 minus sigma 3. So by rewriting the gamma matrices in terms of the spin matrices and by using the high energy frame, and also when we use the high energy limit, the spins of these particles, or the chiralities of these particles become helicities. So we can, like in the Dirac equation in QED, there's a concept called spin, right? And there's also a similar concept called chirality. So we can have a spin up particle that's left chiral or right chiral, and likewise with spin down particles. So chirality, well, let's first write this a spinor. So here is a general spinor solution to the Dirac equation, where we have where we have one left chiral component and one right chiral component. Now, the chiralities for high energy particles become helicities because for high energy particles that are approximately massless, the chirality becomes an invariant aspect of their behavior, and that's the same as helicity. Since helicity is the spin projected onto like the momentum direction, and for like particles traveling at the speed of light, well then it's invariant. That might not make any sense, but just for reference, chirality becomes helicity when dealing with high energy particles. If you guys don't know what those words mean, I made a video on about chirality, so just watch that one. And I haven't made a video on helicity, but there are many sources online about helicity. So with all that said, we can write this equation in a much more simpler form, and that simple form is this right over here. Now we can see where each part of this expression comes from in the Feynman diagram, right? And what's important is that I assume that each particle in the collision has a right helicity or is right chiral. In the actual picture that was given to us, it did not specify the helicities of the particles. So in this analysis, I'm going to assume that they are right chiral. So what we can do now is we can go a bit further to help us simplify what we are going to calculate. So we have an actual collision that's happening here. So we have an electron and a muon that is going to be colliding with each other. Now we can switch to a frame called the center of mass frame where the collision happens head on. So for example, particles in everyday life can hit each other at various angles. So they can hit each other at a right angle, at an obtuse angle, but we can always switch to a frame where those particles are colliding head on with each other. And the same applies in special relativity. So we are going to switch to a frame where the particles are moving towards each other on the z-axis. And since they're moving towards each other, that means that the total 3 momentum is going to be equal to 0. And the reason why it's 0 is because each particle has a negligible mass, and they're moving in the same direction with the same speed, that being the speed of light, well, opposite directions, I should say. So the combined 3 momentum is going to be 0. So our 4 vector for momentum for each particle is going to look like this. So we're going to have ECM over 2, 0, 0, P3. And then for the second particle, P2, so here's like P1 is going to be the incoming electron, and P2 is the incoming muon, so here's P1. For the second particle, we're going to have ECM over 2, 0, 0, minus P3. So what we're saying here is that these particles are colliding head-on with each other in opposite directions. So that if we were to add these two vectors together, P1 plus P2, we are going to have ECM as a result. And ECM is the center of mass energy, which is equal to the combined energies of each individual particle in our scattering process. So I hope that makes sense. And since momentum is conserved, and the particles are colliding head-on with each other, this means that after the collision, the particles should leave at opposite angles with each other. So this is an allowed final state, for example. In the polar coordinate system, the general 4 momentum vector looks like this. Now we can actually find what the angles have to be for the incoming particles to have this to be the form of P1 and this be the form of P2. We can see that if we plot, if we plug in theta P1 to be 0 and phi P1 to be 0, we will have this over here because we will actually have, this will actually be a 1 instead. And this would be a minus 1. And we can see that because if you plug in theta to be 0 and phi to be 0, for P1, we'd have that P1 equals E1, 0, cosine of theta is 0, 0 again, and the cosine of 0 is 1. And then for P2, we would have E, 1, and then sine of theta is going to be 0 again, or sine of pi is 0 actually. And this should be a sine, by the way. Oops, this is a sine. And then 0 again, and then cosine of pi is -1. So that's how we infer the angles of the collision from like the fact that they are colliding head on with each other. So in other words, these are what the angles must be in order for us to have these vectors. And likewise for the outgoing momentum, we can choose these angles over here in order for the 3 momentum to be conserved. And that would give us these vectors right over here. We don't want to specify what theta is going to be because we want there to be freedom for our outgoing particles. So we want the actual outgoing like angle like to like not be predetermined basically. So we already have our setup here. Now we can just go straight in and actually calculate this expression right over here. So let's split it up into 3 parts. So let's start with the red part first. So we can copy that and paste it here. So first we need to find out what URP1 is going to be. This is going to be the right helicity spinor. And I've written the general form for the right helicity spinor. So let's paste our angle bank. So we have theta and phi are 0, right? So UR of P1 is going to be the square root of 2 ECM. So again, the energy is going to be ECM over 2, right? So 2 times square root of ECM over 2 is just going to be the square root of ECM. And since theta and phi are both 2 for the P1 particle, the electron, this means that we are going to have 1 and 0 over here. Now we have to do the same thing for the second particle, the muon. Likewise, we're going to have square root of ECM. For this particle, we chose theta of P2 to be pi. So we are going to be left with, and then we're going to have an I over here, because e to the I pi over 2 is going to be I. So now we have our forms for the spinors for the electron and the muon. All we have to do now is calculate the product. So this over here is a 4 vector, right? So the first component is going to be URP1 sigma naught URP2. The second component, URP1 sigma 1, and you guys get the idea basically. So we want to calculate 4 products, and we're going to stack those products into a row. That's going to give us a 4 vector. So there are 4 calculations that we have to do. And then, of course, sigma naught, the first Pauli matrix is going to be the same thing as the identity matrix, right? So basically, for the first entry, right now we are doing the first entry. So we want to find out what URP1 sigma naught URP2 is going to be. That's going to be equal to, we know that URP1 is the square root of ECM 1, 0. So it's going to be a spin up right chiral particle. And then sigma naught is going to be 1, 0, 0, 1. And then URP2, that's just 0I. It's a spin down particle. And the square root of ECM, right? This is going to give us ECM times 1, 0, 0I. That's going to give us 0. So the first entry is going to be equal to 0. That wasn't so hard, was it? So now we have to calculate the second entry. That's going to be UR of P2 sigma 1 UR of P2. This should be a P1, my bad. And then sigma 1 is going to be, I think it's 0, 1, 1, 0. And then URP2, again, that's just going to be, 0I. So this is going to give us out ECM 1, 0. And then doing the multiplication in our heads real quick. This is going to give us 0. So we're going to have IECM for the second entry. So we know that we're going to have ECM for each entry, right? So we can pretty much just like factor out the ECM. And this is just going to be equal to I, as in the imaginary number. So this third entry, that's going to be a bit more complex to do. It's 1, 0, and the third Pauli matrix. It's going to be this over here, and then 0I, doing that calculation, in our heads, you're going to get a 1 over here. And this is going to give us a 0. So then 1, 0 again. So we get a 1 for the third entry. And then for the fourth entry, it's going to give us like a crazy, insane number. It's going to be UR P1, then sigma 3, UR P2. So 1, 0. The third matrix is going to be 1, 0, 0, negative 1. And then we're going to have a 0I here. And this is going to be like, it's going to be super hard, guys. This is going to give us out 0 over here. And then this is going to give us out whatever number, but it does not matter because it's going to give us 0. So this is going to be the very cool number of 0. So we're done. This is our answer to the red part. So we're going to just copy that and paste it. This is telling us that this is going to be equal to 0, I, 1, 0. Pretty cool, huh? So here we have the blue part, the second part that we want to calculate. So what is URP3 going to be? That's going to be ECM. Then we need to plug in these angles. So theta of P3 is going to be theta. So this is going to give us cosine of theta over 2, sine of theta over 2. And then UR of P4, we are going to have, this is going to be a bit different. We're going to have minus sine of theta over 2, and then cosine of theta over 2. And the reason is by using trig identities. Cosine of theta plus pi, because we're going to have cosine of theta plus pi now over 2. That's just minus sine of theta over 2. So that gives us these over here. And yeah, let's do the same thing. We're going to multiply these together. Now, if you actually went ahead and did the calculation, you would get this over here. It's the same steps as we did before for the incoming spinners. We just use the outgoing spinners instead. So let me just tell you guys the answer. It's this right over here. You have to use a bunch of trig substitutions, and you'd get this over here, basically. So now we gotta multiply these spinners, products, whatever you call them, together. And yeah, let's do that. So we're going to have ECM squared I. So this is going to be our remaining result. We can factor out the I, and we get cosine of theta minus 1. And you guys may think that this is our final answer, but again, it is not, because we have to calculate the yellow part, the E squared over Q squared. So what is that going to be? Now remember from before, like Q is just P1 minus P3, and we are being asked to calculate Q squared, so P1 minus P3 squared. Now there's a nice thing called the U channel. Like for those of you guys that know particle physics, you guys know that this is just the U channel, right? The U channel is just P1 minus P3 squared. And if you were to calculate P1, P2, blah, 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 and square it, you would get this as your answer. Minus E squared Tm over 2 times 1 plus cosine of theta. So this is just the U channel for the process of electron-positron scattering into muons, basically. So what we can do now is simply just plug this back in. And yeah, so we just have to plug this in the Q squared. And this is going to be E squared minus 2E squared over E squared Cm 1 plus cosine of theta. So all being divided by that. And since we are multiplying this product with this over here, our actual answer, the final answer, drumroll please, to the matrix element for electron muon scattering, if they're right chiral, is just going to be I E squared Cm. So I E squared Cm times cosine of theta minus 1. And then times minus 2E squared over E squared Cm 1 plus cosine of theta. and you can see that the center of mass energy just drops out. So the actual energy in which we probe the collision doesn't even affect the amplitude for it happening, which is pretty cool in my opinion. Okay, now what can we do? Well, we see an I over here. The actual observable quantity is a squared element for the matrix element. So the I is just the phase, so it won't really affect that. So we can just drop out that I over there. Doesn't really matter. And what can we do now? Well, E over here, remember from before that alpha, the electromagnetic coupling, is E squared over 4 pi. So E is just going to be the square root or 4 pi alpha, right? So E squared is just 4 pi alpha. Well, here we got E squared times 2. So that's just going to be minus 8 pi alpha, which means that our answer is going to be minus 8 pi alpha times cosine of theta minus 1 divided by 1 plus cosine of theta. Remember the Russian guy said the answer was minus 8 pi alpha, but it seems that he has forgotten the angular term, so you have to add. But this is going to be our full answer over here. Now, if we were to plug in like theta equals pi over 2, for theta equals pi over 2, this is just going to be 1 because cosine of, actually this is going to be 0, right? And then this would be 0 as well. So you would just be left with 8 pi alpha for our answer, which is close to what the guy said in the video, if we assume that the angle is going to be 90 degrees in which they are scattering. So yeah, this is pretty much it actually. Our actual answer for the matrix element is going to be what is in the yellow box, or let's use the red box right over here. Now we can take this matrix element and we can plug it into the formula for the cross section, decay rates, to calculate a new bunch of things. And yeah, so thanks for watching this video. Have a great day and peace out. Bye.